Okay, so we're back to exercise 6. We still have to talk about part G where we actually sketch our graph or try to make a guess and see how good we're at it. Here, here again, here's another example where I'm going to change the scale here to 2 squares being a unit in each case. So it'll be a little bit easier to plot points. And so I have 0, 0 on my graph. I have square root of 3, 0, which is about 1.70. So 1.70, here's 1.5. It's a little bit to the right of that, close to 2. And same thing on the other side here, close to negative 2 is my negative 1.70. Then I have 2, 2, 2, 2. And I have 1, negative 2, 1, negative 2 down here, and negative 1, positive 2. And let's see, finally, negative 2 is right here. And I'm not going to go to Desmos this time. Here, this is actually something called a function, where y is a function of x. And some of you may have had some experience working with functions before. But if we just connect the dots moving from left to right, we get a pretty good shape of this graph. Kind of goes roller coastery, up, down, up kind of shape. And that's a pretty good sketch of this equations graph. And this is an equation that we are actually going to learn a lot about later. It's called a third-degree polynomial graph, and it's going to be really important in what we do later. And now, before we're through with this section, we're going to talk a little bit about symmetry of this graph. If you fold along the y-axis, the two halves do not come exactly together. If you fold along the x, also the two halves do not come together. This graph does not have x-axis or y-axis symmetry, but it has a different kind of symmetry that you can see if we turn the graph upside down. The shape is exactly the same. And graphs that have that property have something called origin symmetry. And I have another picture of a graph, a different graph with origin symmetry. And really the property that defines origin symmetry, it's kind of separate from that turning upside down idea. It's if the point xy is on the graph, then the point minus x minus y is on the graph, the opposite for both coordinates. And notice that when I draw this dotted line connecting those points in this picture, I pass right through the origin. That's why we call this origin symmetry. And yet the easiest way to visualize origin symmetry is just to realize that if I turn this picture upside down, rotate it 180 degrees, the graph will look exactly the same. So because there's this relationship between xy and minus x minus y, you might be able to guess what the test is for origin symmetry. We have to replace both x with minus x and y with minus y and see if an equivalent equation results. So let's go ahead and apply the test to the equation we just graphed. Now we know it does have origin symmetry. So we're going to replace x with minus x and y with minus y. And what do we get? We get minus y equals minus x in parentheses cubed minus 3 times minus x. Or minus x, or I'm sorry, minus y equals, because I'm cubing, that's going to be minus x cubed without the parentheses. And then because I have a negative times a negative, plus 3x. All right, wait a minute. That kind of looks kind of different from our original equation. We did not get the original equation. However, what we have here is actually equivalent to the original equation. So sometimes when you test for symmetry, You don't see the original equation right at this step, but if you can convert by doing the same thing to both sides, if you can convert to the original equation, you've shown that equivalence. And here what I'm going to do is I'm going to multiply both sides by -1. I'm going to take -1 times minus y, and I'm going to take -1 times minus x cubed plus 3x. And to do that on the right, I have to distribute the -1, right? Because there are two terms, so I just want to emphasize that fact that we're distributing. And then I'm going to write the result up here on the right-hand side. -1 times -y is y. When I distribute the -1 on the right, I get positive x cubed. And then negative times positive is minus 3x. Now I have the original equation. So the graph does have origin symmetry. So we didn't see that original equation at that earlier step, but we were able to multiply both sides by -1, which converts to an equivalent equation, which again gave us the original equation. So we were able to verify that that equation has origin symmetry. Now we're pretty much done with this handout. Just want to say a couple things. We just finished exercise 7 here. Some graphs have just one of the three symmetries. Some have more than one. Many graphs have none of the symmetries. Having no symmetry is very common. And a very simple example of that is y plus x equals 3. That's a linear graph that has none of the three symmetries. So that's not at all unusual. In the homework, what I want you to do is take each one of these equations, and for each equation, test for x, y-axis, and origin symmetry. Test for all three. So sometimes you'll have all three, sometimes you'll have none of them, sometimes you'll have some, one or some. Plot a few points, try to draw the graph. Some of these are very difficult. Don't panic if you're unable to draw the graph yourself, but possibly consult a graphing calculator or Desmos to see what the actual graph looks like. And just one last comment is, Desmos is not perfect. In number 10, it's a really strange example that I made up myself because I was trying to stump Desmos, and Desmos gets it wrong. So I have the solutions to all of these are posted in Canvas, and I point out the error in Desmos. So Desmos is not perfect. And so that's it for this section. Sorry, a lot of video content to get us through this one handout, but there was also a lot of good algebra practice too. So we'll move on to functions next.